Welcome to the deep dive. So, today we're jumping straight into large language models, LLMs.
Right.
You've sent over some really fascinating stuff on this. It's moving so fast, this area of AI.
It really is.
And our goal here really is to just pull out the most important bits, give you a clear picture without getting totally lost in the technical jargon.
Exactly. Think of it like we're sifting through it together, highlighting the core ideas, the tech behind them, what they can actually do, and also some of the big questions they raise.
Okay, so let's kick things off with the basics. What are LLMs, fundamentally?
Well, they're essentially very large, deep learning systems.
Right. Part of AI.
Exactly. Trained on just massive amounts of data. But the key thing, I think, is their ability to understand and generate language that feels human.
Yeah, that seems to be the real shift, how we interact with machines.
Absolutely.
Okay.
And thinking about where they fit. You've got AI as the big umbrella. Machine learning is a subset of that, learning from data. Deep learning uses those complex neural networks.
That's right. Multi-layered.
And LLMs are a specific type of deep learning model, sometimes called foundation models now.
Foundation models, okay. Because they're so foundational, so versatile.
Pretty much, yeah. Their capabilities are incredibly broad.
And that term large,
Yeah.
it's almost an understatement, isn't it? Billions, maybe trillions of parameters?
Oh, easily. And that scale isn't just for show. It's why they can learn these really intricate language patterns from all that text data.
Which lets them handle so many different language tasks.
Exactly. And it's interesting to look back, at the history. NLP, natural language processing.
It goes way back. Turing test, mid-20th century.
Right, the idea of machine intelligence. Then you had statistical models, enneagrams in the 80s, 90s.
Predicting the next word, basically.
Sort of, yeah. Then neural nets started making strides in the early 2010s. But the real game changer.
The transformer architecture, around 2018.
That's the one. Models like GPT, Burton. That architecture is really the foundation for almost all the powerful LLMs we have today.
And this isn't just theoretical stuff in labs, is it? Your sources highlight the impact they're already having.
Oh, definitely. Across loads of industries. The potential for efficiency gains, cost savings, it's significant.
And their ability to generate such human-like text has really pushed generative AI into the limelight.
Hugely. So what actually makes them tick? What gives them these capabilities? It boils down to a few key characteristics.
Okay. So number one is that scale, again. Billions, trillions of parameters. That sheer size lets them handle language complexity in a way smaller models just can't.
Right. And tied to that is the pre-training. It's intensive.
They're not just born knowing language.
Not at all. They go through this massive pre-training phase on incredibly diverse text. Books, articles, websites, code, everything.
And that's what gives them that broad grasp of language patterns.
Absolutely critical.
Yeah.
It builds this vast foundational understanding of how language works.
Then there's transfer learning. That sounds important.
It is. It's the ability to take all that general knowledge from pre-training and apply it to new, specific tasks they haven't seen before.
Which makes them super versatile, right? You don't need a new model from scratch for every little thing.
Exactly. It really changes the economics of using AI for language tasks. You leverage these big general models.
And their understanding of context. That seems key too. They can follow along, even in long texts.
Yes, their contextual understanding is vital. They can maintain coherence over extended passages, understand nuance, sentiment, even idioms.
Things that make human language tricky.
Right. And they're not just one-trick ponies. The range of applications is pretty amazing.
Translation, content creation.
Problem-solving, search, summarizing, Q&A, coding. It's a long list.
And you can specialize them further, right? Fine-tuning.
Yeah, fine-tuning lets you adapt a pre-trained model using smaller, specific data sets to make it perform better in a particular domain.
Like for medical text or legal documents.
Exactly. Makes them highly customizable.
Plus, the knowledge seems transferable across languages, too.
Often, yes. The underlying linguistic structures they learn can apply across different languages, which is great for multilingual applications.
And that context maintenance we mentioned, essential for chatbots, right?
Absolutely. Keeping track of the conversation makes the interaction feel much more natural.
They also learn adaptively. They can stay current.
To some extent, yes. They can evolve with new information and linguistic trends. They don't become instantly obsolete.
And creatively. They can actually generate new stuff, stories, music.
They can, learning patterns from existing works and generating novel creative pieces. It's fascinating.
And it's going beyond text now, too, multimodal generation.
Increasingly, yes. producing outputs in different styles, formats, poems, emails, reports, even spoken language, and working with images, audio.
Makes them even more powerful communication tools.
Definitely. Now, to really get how this works, we need to talk about the engine underneath, the transformer model.
Right, the big breakthrough tech.
It really was revolutionary for language processing.
Yeah.
The main shift was moving from processing words one by one sequentially to processing whole sequences in parallel. Much faster, much more efficient. And the core idea, which is quite elegant, is its reliance on attention mechanisms.
Attention mechanisms. Okay, what do?
They allow the model to figure out the relationships between all the different words in the input and output. How relevant is one word to another globally?
So it doesn't need older methods like recurrence.
Exactly. Largely replaced recurrence and convolutions for sequence tasks in NLP.
And transformers aren't just for language now, right? They're used elsewhere.
That's right. They've achieved state-of-the-art results in computer vision, speech recognition, time series forecasting. Surprisingly adaptable.
So the basic structure has two parts, encoder and decoder.
Correct. The encoder's job is essentially to read and understand the input text.
Turn it into something the model can work with.
Yeah, into a representation that captures the meaning and relationships between words.
And the decoder.
The decoder takes that understanding from the encoder and generates the output sequence, word by word.
Okay, let's break down the encoder a bit. It's made of layers.
A stack of identical layers, yes. And each layer has two main parts, a self-attention mechanism and a feed-forward network.
Self-attention. That sounds like the core of the attention idea.
It really is. It lets the model weigh the importance of different words in the input sentence when processing a specific word.
How does it do that weighing? I saw something about query, key, and value vectors.
That's the mechanism. For each word, it computes these three vectors. You can sort of think of the query as what the current word is looking for.
Okay.
The keys are like labels on all the other words saying, here's what I represent, and the values are the actual substance or meaning of those words. The attention mechanism calculates scores based on how well the query matches the keys.
To decide which other words are most relevant.
Exactly. Those scores determine how much weight to give to each word's value when representing the current word.
Right. And then that info goes through a feed-forward network.
Yes, to process those weighted representations further, extract more complex features.
And because it's all parallel, it needs positional encoding to know the word order.
Crucial. Otherwise, dog bites man looks the same as man bites dog. Positional encoding adds information about each word's position in the sequence.
Got it. Now the decoder. Similar layers, but some differences.
Similar structure, yes, but it has masked self-attention.
Masked.
It means when predicting the next word, it can only attend to previous words in the output sequence, not the words it hasn't generated yet. It can't cheat by looking ahead.
Makes sense. And it also pays attention to the input.
Yes. That's the encoder-decoder attention layer. It helps the decoder focus on the relevant parts of the input sentence as it generates the output.
And then a feed-forward network again?
Correct. So the decoder uses the encoder's output, the words it's already generated, and its attention mechanisms to predict the next word step by step.
Until it hits an end signal.
Exactly. So it's this interplay between encoding the input and decoding to generate the output, all powered by attention.
And these attention mechanisms are really central, self-attention especially.
Absolutely. Understanding relationships within the sentence itself, calculating those query key value vectors, comparing queries to keys to get attention scores, normalizing those scores into probabilities, and using them to create a weighted sum of the value vectors. That's the core calculation.
And then there's multi-head attention. What does that add?
It makes the model more robust. Instead of just calculating attention once, it does it multiple times in parallel, each with slightly different learned perspectives, different heads.
Like looking at the sentence from multiple angles.
Kind of, yeah. Each head focuses on different types of relationships or information subspaces. Then it combines the results for a richer understanding.
Okay. And positional encoding, just to recap, absolutely necessary because processing happens all at once.
Precisely. Without it, the model loses the sequence order. Positional encoding adds a unique positional signature to each word's embedding.
And finally, residual connections and layer normalization. These help with training these huge networks.
They're critical for training deep networks effectively. Residual connections, or skip connections, help the learning signal flow better, avoiding vanishing gradients. And layer normalization stabilizes the activations within the layers, preventing them from getting too large or small, which helps the learning process converge.
So it's a complex combination, but it all works together. Okay, let's shift to training these beasts. Sounds computationally massive.
Oh, it is hugely intensive, needs vast amounts of data, sophisticated techniques.
And the data comes from everywhere. Books, websites, code.
Pretty much. Diverse sources,
Mhm.
books, articles, websites scraped from the internet, large code repositories.
We saw mentions of data sets like Commentrol, the Pile, C4, huge collections.
Massive ones. And things like Refined Web, trying to improve quality. Starcoder data specifically for code. Book corpus. Roots. Wikipedia is often in there.
Red Pajama, too, the open source Llama dataset recreation.
Right. And besides these general data sets, you have task-specific ones for fine-tuning, like Squad for question answering. Yeah.
Data quality and transparency seem like big issues there, too.
Increasingly so. Knowing what's in the data is important, but the main training technique itself is usually self-supervised learning.
Self-supervised, meaning it learns from unlabeled data.
Exactly. No need for humans to label everything.
Wow.
The model learns by predicting parts of the data itself, using pretext tasks.
Like masked language modeling, MLM.
That's a common one. You mask out, say, 15% of the words, and the model has to predict them based on the surrounding context, forces it to learn relationships.
And the other one, next sentence prediction, NSP.
That trains it to understand discourse. Given two sentences, does the second one logically follow the first? Helps with coherence.
So after this huge pre-training, you fine-tune it for specific jobs.
Correct. You take the pre-trained model and train it a bit more on a smaller, task-specific data set, adapts its general knowledge.
And techniques like RLHF, reinforcement learning from human feedback.
Yes, that's a key fine-tuning strategy. Using human preferences to guide the model towards generating outputs that are more helpful, honest, and harmless.
And instruction tuning, teaching it to follow commands.
Right. Training it specifically on examples of instructions and desired outputs.
So pre-training builds the foundation, fine-tuning shapes the specific skills. Okay, let's talk about those skills. What can they do? Seems like a lot.
It is a lot. Because of that training, they're incredibly versatile. Real Swiss Army knives for language.
Text generation is the obvious one. Articles, stories, emails, code.
Right. Generating coherent, contextually relevant text in various styles. Completing prompts, writing documentation, creative writing. Models like ChatGPT, Claude, Llama 2 excel at this.
In translation, they're good at that.
Very effective. High accuracy, fluency, handling idioms and nuance. Really breaking down language barriers, especially multilingual models.
Text summarization, too. Condensing large documents.
Yeah, incredibly useful. Taking huge amounts of text and boiling it down to the essentials. Capturing the key info. Big value in research. Business.
Can they do extractive, just pulling sentences, or abstractive, writing new summaries?
Both. Abstractive is often more sophisticated, generating novel sentences to summarize.
And question answering, using their training data as a knowledge base.
Exactly. Responding to queries in natural language by accessing and processing the information they were trained on, even synthesizing answers from multiple points in the data.
And the code generation aspect is fascinating, writing code from descriptions.
Yeah, generating snippets, functions, even whole modules, analyzing existing codes, suggesting improvements, translating between programming languages. Huge for developers.
And they can often do new tasks with just a prompt, zero-shot or few-shot learning.
That's the power of transfer learning again. They generalize remarkably well sometimes.
And sentiment analysis, understanding emotional tone.
Yes, figuring out if text is positive, negative, neutral. Great for customer feedback, market research, brand monitoring.
So, truly multifaceted. Okay, but they're not perfect, are they? What are the limitations and challenges?
Definitely not perfect. Despite their power, there are significant limitations.
Bias seems like a big one. Inheriting bias from the training data.
A major concern. If the training data contains societal biases related to gender, race, etc., the model can learn and even amplify them, leading to unfair or discriminatory outputs.
Requires careful data curation and auditing.
Absolutely. And then there's the issue of factual inaccuracies, hallucinations.
Right. They can sound confident but be completely wrong.
Yes. They might generate text that's plausible sounding, but factually incorrect or inconsistent with the input. It can stem from data issues or the model's probabilistic nature.
And understanding why they produce a certain output, interpretability is hard.
Very hard. They're often black boxes. Difficult to trace the reasoning, which raises concerns about trust and accountability, especially in critical applications.
And they need massive computing power, right? High costs.
Enormous computational demands. Training and running them requires significant processing power, memory, energy. High costs, which can limit accessibility.
Okay, so real challenges alongside the capabilities. Where are we seeing them used most effectively right now across industries?
They're popping up everywhere, really transforming operations, automating tasks, enhancing customer interactions, improving decision-making.
Content creation and marketing seem like a natural fit.
Definitely. Automating blog posts, ad copy, social media, generating product descriptions, personalizing marketing messages, brainstorming, SEO optimization.
And customer service,
Yeah.
chatbots and virtual assistants.
A huge area.
Yeah.
Powering intelligent bots for 247 support, instant responses, personalized help, analyzing customer sentiment from feedback.
What about R&D research?
Yeah, accelerating knowledge discovery, summarizing research papers, analyzing reports, finding patterns in data, even helping formulate hypotheses.
And healthcare. That
Yeah.
seems sensitive.
It is, but the potential is there. Generating clinical notes, summarizing patient histories, potentially suggesting treatment avenues based on data, even aiding drug discovery by analyzing biological data. Diagnostics and image interpretation are being explored too.
Accuracy is paramount there, obviously.
Absolutely critical. Needs extreme caution and validation.
Finance and banking, fraud detection, risk assessment.
Yes. Identifying fraud patterns, assessing financial risks, automating compliance checks, offering personalized financial advice potentially.
And education, personalized learning.
Another big potential area, AI tutors, adapting to student needs, generating educational materials like quizzes or lesson plans, providing feedback on writing or code.
And I imagine supply chain, software development, legal fields too.
All seeing applications. Optimizing logistics, improving coding workflows, assisting with legal research and document review. Their language ability is fundamental.
It really touches almost anything involving text or communication.
Pretty much. It's a core capability with broad applicability.
Which inevitably brings us to the ethical considerations. These seem critical.
Absolutely critical. As they become more integrated, the ethical questions become more urgent.
Like the potential for misuse, generating harmful content.
A major risk.
Yeah.
Creating misinformation, fake news, sophisticated phishing scams, hate speech, propaganda, prompt hacking to bypass safety controls is also a concern.
And the economic impact, job displacement.
A significant worry. Automation of language-based tasks could displace workers, potentially increasing inequality. Need for retraining, social safety nets becomes important.
What about privacy? They're trained on vast data.
Yeah.
Some of it must be personal or copyrighted.
Huge issue. Training data can include personal information, copyrighted works, sensitive business data, raises questions about consent, ownership, and the potential for the model to regenerate or reveal sensitive info. Robust security is vital.
So it all points to the need for responsible AI development.
Essential. Ensuring these models are trustworthy, transparent, accountable, and secure. We need clear ethical guidelines, regulations, ongoing research to mitigate the risks and make sure they're used beneficially and fairly.
It's a complex balance between innovation and responsibility.
It really is.
Well, this has been a fascinating deep dive. We've covered a lot what LLMs are, the transformer architecture, the massive training involved, their incredible capabilities, but also the limitations and ethical considerations and how they're spreading across industries.
They definitely represent a huge leap in AI. Immense potential, but paired with some really significant challenges we need to navigate carefully.
Absolutely. So as we wrap up, here's something to think about. Given how fast things are moving, what do you think might be the most unexpected way LLMs weave themselves into our daily lives in, say, the next few years?
That's a good question.
And alongside that, what ethical challenge do you think will demand the most urgent attention as that integration happens? Lots to consider there.
Definitely food for thought. Finding that balance is key.
It really is. Thanks for joining us on this deep dive today.